Quantum computing is a revolutionary form of computing that leverages the laws of quantum physics, the same science that explains how atoms and subatomic particles behave. It's not just a faster computer, it's a completely different kind of computer that can tackle problems classical computers can't efficiently solve, no matter how powerful they are. Classical computers use bits, where each bit is either a 0 or 1. They perform calculations in sequence or with limited parallelism. These machines are great for things like word processing, web browsing, gaming, and so on. Now, quantum computers use qubits. A qubit can be 0, 1, or in a superposition, which means both 0 and 1 at once. Thanks to superposition and entanglement, quantum computers can perform multiple calculations simultaneously. They're really good for simulating molecules, optimizing systems, factoring large numbers, and more. Let's talk about qubits, or quantum bits. A qubit is the fundamental unit of quantum information. Unlike a bit that is either 0 or 1, a qubit can be in a blend of 0 and 1 at the same time. That's called superposition. Qubits can be built using photons, ions, electrons, or superconducting circuits. Superposition means a qubit can exist in multiple states at once. For example, instead of flipping a coin that lands on heads or tails, it's like the coin is in both states until you check. This allows a quantum computer to evaluate many possibilities at the same time. Now, let's look at entanglement. Entanglement is a strong connection between qubits where the state of one immediately affects the state of the other. Entangled qubits behave as one unified system, even when physically separated. This allows for powerful correlations that are impossible in classical systems. And then there's interference. Quantum computers amplify the probabilities of correct answers and cancel out the wrong ones using interference. Think of it like tuning radio signals. Constructive interference strengthens the signal you want, and destructive interference cancels noise. Quantum computers can solve certain problems exponentially faster than classical computers. Here are a few examples. In cryptography, quantum computers can break classical encryption, like RSA using Shor's algorithm. For drug discovery, they can simulate the quantum behavior of molecules and atoms. When it comes to optimization, quantum computers can explore all possible configurations faster, like finding the shortest route or the best investment strategy. And in machine learning, they can accelerate tasks like pattern recognition and clustering. Quantum computing is not ready for everyday use yet, so here's why. First, let's talk about the fragility of qubits. Qubits are extremely sensitive to their environment. Even a bit of noise, heat, or the slightest interference can cause errors, which are called decoherence. Error correction is another big hurdle. Quantum errors are actually pretty difficult to detect and fix. Scientists are working on quantum error correcting codes, but, well, they require many extra qubits just to protect one. Then there's scalability. Building quantum computers with thousands or even millions of stable qubits is, honestly, still a huge engineering challenge. And finally, cooling requirements. Most quantum computers need temperatures close to absolute zero, that's minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. This demands some really complex cryogenic systems. So, several companies and institutions are, really leading the way in quantum computing development. IBM, for example, offers cloud-based quantum computers through something called IBM Quantum Experience. Google actually achieved what's known as quantum supremacy back in 2019. Microsoft is working on these things called topological qubits, which are supposed to be more stable. D-Wave focuses on quantum annealing, mainly for optimization problems. Rigetti provides cloud-accessible superconducting quantum processors. And of course, academic labs like MIT, Caltech, Harvard, and others are constantly pushing the boundaries of quantum theory and experiments. Alright, so to actually program a quantum computer, you need a different set of tools and languages. For instance, Qiskit, which is developed by IBM, is a Python framework that lets you write and run quantum code on IBM's systems. Cirq from Google is another Python library, but it's mainly for building and testing quantum circuits. QTIP is used to simulate quantum systems and is often used for research purposes. And then there's Ocean SDK by D-Wave, which is a toolkit specifically for working with quantum annealers. Quantum computing isn't going to replace classical computers. Instead, it's going to be, well, a specialized tool for certain types of problems. Looking ahead, quantum computing might revolutionize medicine, like by enabling personalized drugs. It could make current encryption methods obsolete, which means we'll need something called post-quantum cryptography. It might also really accelerate AI and machine learning and help us honestly better understand fundamental physics. If you're interested in getting into quantum computing, here's a simple learning path to get you started. Step 1 is to understand the basics, so learn about quantum mechanics, especially concepts like superposition and entanglement. You'll also need to understand linear algebra and complex numbers, since those are essential for working with quantum gates. Step 2 is to explore quantum algorithms. You should study famous algorithms like Shor's algorithm for factoring, Grover's algorithm for searching, and the Deutsch-Joscha algorithm for problem classification. Finally, step 3 is to start coding. You can use IBM's Qiskit tutorials or Google's Cirq notebooks and try running simple quantum programs either in simulators or on real quantum hardware. IBM, for example, offers free access to their systems.